Hi, everyone. So now I'm going to talk to you about a security analysis system for Ethereum smart contracts, which we have developed at the SRI lab at ETH Zurich. So this is a joint work with Andre, Dana, Arthur, Florian, and Martin Vecev. So before I jump into the topic, I want to make sure that we are on the same page and know what a smart contract. So smart contract these are basically typically small programs that own and handle cryptocurrencies. So for example, here you see a smart contract that's where users can deposit some funds. So there's this balances field that keeps track of how much funds users have. And then it also has this withdraw function that allows users to get the money they have deposited. So in more detail, what the withdraw function does is it first reads the balance of the transaction sender. So here message sender returns the address of the transaction sender. Then it sends the money to the transaction sender using this call instruction. And then it sets the balance of the user down to 0 to know that the money has been withdrawn. So these kind of contracts are typically written in high-level languages, like this, for instance, is written in Solidity. And an important thing for security is that once you write these contracts and you deploy them on the blockchain, typically there's no way to update them. So this really means that if there would be any, you have to make sure that there are no security vulnerabilities before you go to deployment on the blockchain. So what can go wrong when programs start handling billions worth of USD? What happens is that every few weeks, there are news headlines that talk about bugs in smart contracts. So the first major security bug in Ethereum that happened was the DAO hack, which happened in 2016. So this bug allowed an attacker to steal 60 million worth of Ether. And this was really kind of the first time people realized that, wow, smart contract security is really important, and we have to put some effort to make sure we can find these vulnerabilities. And after this first bug, so there were many other security issues. So last year there were several critical security bugs in popular Ethereum libraries. And as I said, these are very frequent. So the last bug was just exactly a week ago, last Tuesday. So before I proceed, I want to give you a concrete example of a security bug. So I picked the DAO bug because it was the first one, and then I'll use it overall to show you why it's hard to find these bugs and how we approach this problem with the Securify system. All right, so the DAO hack it's about a bug in this DAO contract, which allows, again, users to deposit money and then to withdraw all the funds that they have deposited. This is a much simplified version, but it's enough to understand what's going on. So there are other smart contracts that can interact with a DAO contract. For example, this user contract here has this function foo that would end up calling the withdraw function in the DAO contract to get the money out. So imagine that the user contract has deposited 10 Ether in the DAO contract. If we call foo, then we would call withdraw. The DAO contract would transfer back the 10 Ether back to the user contract. And then later on, if we make another transaction with foo, there would be no Ether sent to the user contract because the balance at this point is 0. All right. And the question is, well, can the user contract do something different to get more money than it has deposited on the DAO contracts? And that's somebody figured out that is possible. And here's why. So it's really important to understand what the semantics of these contracts is. So the money sent back to the user contract is sent using this call instruction. And if we carefully look at the semantics, this actually ends up transferring control back to the user contract and calling this default function. Okay, so this is typically useful because you can log that the payment has been made. That's the reason it's there. And we can also, what the attacker observed is that the balance of the transaction sender is set to 0 only after the call instruction terminates. So if the attacker was smart enough to figure out that you could actually, in this default function, write it in a way where you would call back the DAO contract, again, the same withdraw function. And then this second call would go through with the same original balance of the user. So if we run this, basically, we call the foo function, we get a withdraw from the DAO contract for 10 Ether. Immediately, this is followed with another call to withdraw. The Ether amount is still 10. So this will keep going on forever. So in practice, the user contract would bound how many times this recursion happens. So it's, let's say, after 10 times you do the withdrawal, you would stop. So you would get 10 times the amount of money you have deposited. And that's exactly what the attacker did to steal a lot of Ether from this DAO contract. So this was just one example of a critical security bug. And there are many other ones. I have listed some of them here, like unprivileged rights, unsafe use of unsafe inputs, and so on. And overall, together, last year, these bugs resulted in over 300 million lost of 300 million worth of USD lost due to these security issues. So clearly, we have to do something about this problem. So what do we want to solve this problem? Okay, ideally, you would want to come up with some automated system, or you could put the smart contract and then it would pinpoint precisely what the vulnerabilities are so we can fix them before we deploy the smart contract on the blockchain. And there are several challenges and limitations involved if we want to build such a system. So let me show you why this is not so trivial. So here again, we have the DAO hack. Okay, the problem is that we have the balance is set, the state is changed only after the call instruction terminates. So an example of security property we may formulate to detect this kind of bugs is that we don't want to have state changes after the call instruction. Okay, so imagine we care about the security property. And then if you take a smart contract, you can basically classify all the calls in the smart contract into safe and unsafe, depending on whether they violate or satisfy the security property. So the immediate question is, well, can we automatically find all the unsafe calls in the smart contract? That's what we would want. Sadly, the answer here is no, because the smart contracts are typically written in Turing-complete languages, which means that it is undecidable to check arbitrary properties on arbitrary contracts. And as a way to deal with this problem, existing solution basically focus on bug finding. So they focus only on fuzzing or doing symbolic execution, different techniques that allow you to under-approximate the behaviors of the smart contract and then report whatever bugs you find in the smart contract. The limitation of this is that you would end up missing some of the vulnerabilities because you would not get full coverage over the contract. And in the context of contracts, that's not really desirable because, if you deploy and you miss the bug, there's, it's just hard to fix it afterwards or impossible. So we want to do better. And so what we did is we actually looked at many different real-world contracts, and we looked at why they satisfy or violate relevant security properties, and we had the following insight. So very often when a contract satisfies or violates a property, it also tends to satisfy or violate a much simpler property or a pattern. Let me tell you what I mean by this. So this is, again, back on the same example, this DAO hack. So if you want to prove that a call is safe, you can essentially inspect the control flow graph of the smart contract and check that there are no writes that can follow the call instruction. Okay, you can look at the CFG and figure this out. And it actually turns out that with this compliance pattern that proves safety of the call, you can verify 91% of all the call instructions in Ethereum smart contracts. So it's pretty powerful way to prove safety for this property. So it will not catch all the safe calls, but a big amount of those. And conversely, you can also come up with violation patterns that can match instructions that are guaranteed to be violating this security property. So for instance, if you have a write and this write is always followed by a write to storage, then you know that for sure if this call executes, it would violate the security property. So based on these insights, we have built this Securify system, which is available on this address I showed you. And it's publicly available. You can go to see how it works. And essentially what the system allows is people can submit they just can paste the code of the smart contract. And then they can scan their contract with the system, and then below the system would produce a comprehensive security report. So it supports 18 different critical vulnerabilities, and it would pinpoint the precise locations where these vulnerabilities are detected. For instance, the red here would mean that at this line 62, definitely there is some kind of issue. So this is the example where you have the states change after the call instruction, and again here this would be highlighted to know that there's an issue it has to be fixed. Okay, so you're free to try out the system. And we released the system, the full version of the system was released actually a few months ago. And since then, today it's really used very regularly by many security auditors that are auditing smart contracts. We have over 1,000 subscribers that are signed up for new versions of the system. And now it's actually, the system was also officially funded by the Ethereum Foundation, which will support the further development of the system and integration of the system with other tools for the Ethereum platform. So based on this, the chair mentioned, also we have incorporated a startup to develop this and other systems in this space to secure smart contracts code, chain security. Okay, so let me give you a bit of insights on how this system works under the hood. So here's how the analysis goes. So the system works directly on the bytecode of the smart contract. So it starts with the EVM, and this is stack-based representation. It's kind of hard to analyze directly. So as a first step, we decompile it, and we put it into an intermediate representation that is more suitable for analysis. And then we analyze this representation, and we derive different kinds of semantic facts about the different kind of semantic facts that hold over all executions of the smart contract. So intuitively here, we want to capture pieces of information that are relevant to either prove security properties or find violations in these of these security properties. And then finally, the system applies different kind of compliance and violation patterns to find actual violations or compliances of these security properties. And then it produces this security report and gives it to the user. So important here to notice that these patterns are written in a specific domain-specific language to allow us to quickly add new patterns as we learn about new vulnerability issues in Ethereum contracts. So next, I will briefly go over what are the key insights that we use in these steps. I will not go in too much detail. Of course, you can always check out the paper to find the full details. So the compilation step is fairly straightforward. Here we use a static single assignment form to make it easier to analyze the representation. And we recover the control flow structure of the smart contract. And we do a lot of standard tricks like partial evaluation, method inlining to make sure that the analysis is as precise as possible. Then when we infer the facts, so this step is fully encoded in stratified data log. So stratified is this logic-based language that can easily reason about recursive queries. So let me give you an example of what this analysis looks like in Securify. This is a very basic example where, let's see, so we have this data log program. And what this program, it has two rules. So it takes as input this follow predicate, and then it computes the transitive closure of this predicate. All right. So what you can do with this program is you can run it to check reachability of instructions in the smart contract. For instance, you would start with the intermediate representation, then you would derive which instructions immediately follow each other, and then you can feed this input to the data log program and infer the transitivity over the reachability of these instructions. For instance, you would figure out that here in this example, instruction at line 6 could follow the one at line 1, and so forth. So that's a basic example how this works. In the actual Securify system uses more fancy, more complicated, infers more complex predicates. Like there's also must analysis for basically where you want to show that instructions definitely must follow each other, and also does different data flow analysis to figure out how variables depend on each other and so forth. And in this inference fact step, the main thing that we leverage for data log is that if you take the real world smart contracts, you would end up inferring millions of such facts. So you need to leverage something that's pretty efficient if you want to apply this for realistically large smart contracts. All right, the last step, basically using the semantic representation, we infer facts using patterns. I will not go into too much detail on what these patterns are, but basically you can write arbitrary logical formulas over the predicates that are inferred with this over these semantic predicates. So let me give you an example of what this looks like. Again, on the DAO hack, where here the relevant property for this example was we want to make sure that there are no state changes after call instructions. And for this example, the compliance and violations pattern would look as follows. So for compliance, we can write that a contract is safe if any call instruction is not for any call instruction, there's no store instruction that may follow it. And conversely, for the violation, we can phrase the pattern saying that if there exists a call and an store where the store must follow the code, then for sure the property would be violated. So what we can then do is we can manually prove that a match of the compliance pattern would give you a satisfaction of the security, the original security property. And you can also prove the same for the violation, that if you match the violation pattern, this implies the negation of the security property that we care about. So how are these patterns useful? This is how Securify produces its reports. So any call matched with the compliance pattern would be reported as a violation because the system guarantees that that's actually a violation. And then it would filter out all the calls that were matched with the compliance pattern because we know that these were definitely not issues. And everything else would be reported as a warning because then the system couldn't figure out if it satisfies or violates the property. And to be on the safe side, we report it to the security expert to figure out if this is a false positive or a true positive. So the important point here is that all unsafe calls will be reported as one of these two kinds, either a violation or a warning. So in the paper, we also define different seven relevant security properties. We define their patterns and prove the logical relationship between these patterns and these properties. All right, so I will give you a little bit of results on how the Securify system performs in practice. So I will answer two questions. So the first one is I'll show you how precise Securify is for relevant properties and contracts, and then I'll compare it with several other security checkers for Ethereum smart contracts. So to do this evaluation, we took, as a data set, we took 100 real-world smart contracts that were uploaded to the front end of the system. So we took the first 100 contracts submitted in 2018, and then we took 9 critical vulnerabilities, and we measured the violation, how many of the behaviors are classified as violations, safe, or as warnings, and then to also get a better feeling on whether the warnings tend to be false positive or true positive, because this indicates kind of which pattern is not precise enough, the compliance or the violation. We split those into true warnings and false warnings. So here's the data that we got for these vulnerabilities. So here for each, there are several bars. Each bar corresponds to one security property. There are several segments. So the red segment indicates the fraction of violations found by the system. And then the shaded parts are the warnings, which is, this part is split into, I guess I mentioned, into true warnings and false warnings to see what's going on. So something to notice that the white part here is also important. Okay, so for the last property, for instance, this white part here indicates that 90% of the contracts were verified to satisfy this property. So in this case, this is locked Ether, which guarantees that users cannot lock Ether in the smart contract. So another thing we also observe in the result is that for some of the properties, the system is actually very precise, and it can always match one of the two patterns, and this resulting in no warnings in this case. And overall, so for 6 out of these properties we considered, there were less than 10% warnings, meaning that the patterns actually match in many of the common cases. So here I show you how we also run 2 other systems. So we run Oyente and Mithril, which are systems based on symbolic execution. So we consider 4 different properties because these were properties that were supported by these different systems. And one thing to note here is that there's also this other segment, the black segment, which indicates vulnerabilities that were not reported by the tools. So this was important because these other tools can also have unreported issues. And so what we observe here is that actually the symbolic tools surprisingly tend they fail to report fairly large fraction of the actual vulnerabilities present in these contracts. So that was one observation that we made. And surprisingly, some of the symbolic tools, they have large number of false warnings, which in theory you could avoid if you have very precise symbolic interpreter. But this didn't turn out to be the case, and we observed fewer false warnings using our static system. All right, so with this, I'm going to conclude. Here's like the key things that you observe I presented to you during the talk. Thank you for the attention, and I'll be very happy to take any questions.
Hi. It's working? Yeah. Hey, Alejandro from Chalmers University. Yeah, I wonder if you can. I would like to know if I'm a security expert and I write down a property. Can I characterize by just looking at the property if your tool is going to give me a lot of true positive or true negatives? Because here you show TA and TRT, but is there any pattern that I can use to predict if your tool will behave properly?
Yeah, I think, thanks. So the question is basically if you have a property, how easy it is to know if the Securify would give you lots of warnings.
Right.
So for some, it depends on, there are cases. For instance, if you look at like more numerical properties like overflows, so these are things that we don't currently do. So basically you just don't have the semantic information to check these properties. So you would really have very coarse pattern that would definitely give you lots of warnings. But there's no systematic way somehow to do this, or at least I'm not aware of how to do this in a more automated way.
All right, thanks.
Hey. All right, great presentation. Quick question about slide number 13, I believe it was, let's assume that we happen to have a very complex function where a function call of calling a function, then changing a balance doesn't happen immediately. And there could be a, I don't know, 20 other statements in between. How do you go about, how flexible is your system? Do you have to go, may follow one step, may follow two steps and so forth, or you could make it more intelligent so that it could make the connection?
Yeah, sure. So basically what the system does is it would transitively look at, so it would transitively look at how instructions may follow or not, or must follow each other. So it would cover this case where instructions are very far away. What can happen is if you have very complex logic on basically data dependence branches where you would have infeasible paths and so on, then what could happen there is just the pattern would not be, the analysis would not be precise enough, and it would give you a warning because it's not feasible to, it's not possible to verify or violate it precisely.
Thank you.
So great paper. I'm very happy to see open source tools on smart contract security. I want to ask you about evaluation of your paper. There is a section in which you said you evaluated with contracts directly from the blockchain. I think it was missing on the presentation.
Yes, I didn't show that part.
Okay, so you in the paper said that you took 20,000 contract from the blockchain. How did you select this? Because one of the things that are usually in the evaluation when people do papers on blockchain, they took directly the contracts from the blockchain without any filtering. And if you do this, you will have a lot of people that submitted contracts just to test, and you will have a lot of results finding varieties that are not relevant, in fact. So did you make some filtering, especially amount of ether and amount of transactions?
Yeah, good question. So, I mean, we wanted to avoid any bias, so we took these contracts, basically we parsed the blockchain and we took consecutively deployed contracts. So this avoids any bias because we just took like between two blocks, all the contracts deployed. So there was no filtering in that sense. Same for the other evaluation where we picked again consecutive contracts where we would not cherry pick specific contracts.
Okay, and are you going to release the source code? The data set that you use? Or maybe the blocks, the number of blocks.
Yeah, I can release the blocks for sure. For the other data sets, so these things were uploaded to the system. So I'm not sure we have the rights to publish them, but if we signed something, I can for sure give them to you.
Okay, thank you.
Yeah.
Hi, Itayal from the Technion. Thank you for the presentation. I wanted to ask, the system reports on potential errors and it reports in your intermediate representation. Mm-hmm. How easy is it for the developer to translate that into the lines that they need to fix in the Solidity code?
Yeah, so the system already does this mapping. So these violations here are directly reported on the Solidity code. So we have basically mapping from bytecode offset to intermediate representation instructions down to back to Solidity. So this is fairly straightforward. The only issue is sometimes you have bytecode offsets that don't correspond to Solidity lines. So these are things introduced by the compiler for some intermediate computations. And there you would have to basically be debugging at the bytecode level because it doesn't have meaningful representation at Solidity.
Thank you.
There's time. Have you tried, you write this over approximation and under approximation patterns. Have you tried formally connecting those to this property that I guess currently exists like in someone's head, but have you tried writing that property down and really proving that the three things connect?
So we have formalized a security property at the level of EVM, like some trace properties, not at the level of, I don't know if there's some other level that you're thinking about, like more high level. This we haven't just done, but we can discuss to see exactly what you mean. And yeah.
Okay, great. Let's thank the speaker again.